All right, guys, we have now reached the most anticipated and important part of our class today because now we will be discussing cognitive loading, specifically the context in which ACER will ask you this, meaning interconnected tables, diagrams, graphs, and a whole bunch of data. All right, so cognitive loading goes hand in hand with data interpretation, and I can confidently tell you that at least 60% of your GAMSAT will be cognitive loading in the context of data interpretation. So right now, I've got Unit J before you, and I'll begin by giving you an overview of sort of how ACER will be presenting such questions. At the start here, what you have is a three-dimensional axes diagram, and following this, you've got a couple questions, right? So the first part of this STEM involves you understanding how this 3D axis diagram works and really mastering your consolidation of the variables that are being presented in this diagram. Then you have a table and another diagram. And you don't just have a table and another diagram, you actually have another graph. Okay, so right off the boat, they are heaving you with a bunch of information, which is, of course, all contextually relevant and anchored to the very first diagram that they gave you before. This is a true example of cognitive loading because it shows you how, firstly, a lot of this data is quite interconnected, but it's being heaped on you, heaped on you, heaped on you. Almost like what you'd expect as a day-to-day working doctor in clinical medicine, where you've got to consider all of this information and anchor it in some way. Then you've got a couple questions that will really test if you have consolidated those rules from the above diagrams. And then another table, which again is a form of cognitive loading on top of the data before, and more questions, right? In the modern day GAMSAT, you're going to be asked a lot of these cognitive loading stems, and I would confidently tell you that at least 60% of the GAMSAT is cognitive loading data interpretation, possibly more. And most of the time, when you're being asked these questions, as at least for the recent GAMSATs, like the most recent one that was sat in March 2025, and even the September GAMSAT last year in 24, most of the time, these cognitive loading questions will have three data sets and at least 4 to 5 questions in the STEM. So that is how cognitive loading is presented. I'll now get started by actually defining the scientific principle behind cognitive loading. Okay. So cognitive loading, how does it work? Suppose in the first data set, you have the following variables, X, Y, and Z that they've presented before you, right? Then suppose in the second data set, you've got A, B, and Y. Okay, so two new variables, but one carried over from the data set before. And suppose in your final data set, you have the following new variables, okay? H, I, and B, all right? This is a very simplified scientific format, right? Because I've simply just listed 9 independent variables, but it is relevant, especially because if you break it down like this, it's easy to understand what cognitive loading is really asking you for, okay? Because what's the pattern here? The pattern here is that Y overlaps, and from 2 to 3, B overlaps. So due to this overlapping pattern, what's the greater implication here? The greater implication is that you've anchored yourself in some way, okay? You've anchored yourself through seeking out a common variable between every single data set, and therefore you've given everything some sort of contextual relevance, right? Because Y is carried over from data set 1 to 2, this means that variables A and B can be compared directly to X and Y, all right? Between data sets 2 and 3, because B is carried over, that means H and I can be directly compared to A and Y. And because of the rule before, Y being carried over, H and I can also be compared to X and Z, all right? So what is cognitive loading? Cognitive loading is simply a method of tracking, okay? Please be mindful of this. Please even write this down, all right? Cognitive loading is actually a method of tracking common variables, right? It is a method of tracking common variables so that you can draw contextual relevance to all of the other independent variables, right? By tracking these common variables, new information that is presented down the track will make sense in light of the information presented upstream, okay? Therefore giving you a holistic understanding. So with that definition of cognitive loading out of the way, let's actually try this stem, all right? It's quite a long stem. I'm gonna do the questions that are truly relevant towards your understanding of cognitive loading, all right? So the texture of a soil is measured by the relative percentages of sand, clay, and silt, right? Sand, clay, and silt. Figure 1 illustrates the classical representation of the composition of soils whose common names are within the boundaries shown. Let point X represent a soil called sandy loam. That is 60% sand, 25% silt, 15% clay. So here we have a 3D axis diagram. Right, so point 1, we need to actually understand how this 3D axis diagram works, right? So we can do so by using this pointer X, okay? We have percentage clay, silt, sand, but we don't know how the axes are oriented. We don't know if sand goes, this way or that way or that way, okay? But we can figure it out using this pointer X. So they've shown you point to X, and they tell you that it's 60% sand. All right, so the only way it can be 60% sand is clearly if you go that way, right? 25% silt. So 25% silt if you go that way, 15% clay if you go horizontal transverse. So the orientation of your axes are as follows, right? That is for clay. So if you go horizontal to the left, it's clay. Oblique to the right is silt, and oblique down to the right. So oblique down to the right is sand. All right, let's do question 1. In a bucket of sandy loam, if a bucket of sandy loam having the characteristics of point X in figure 1 is mixed with a similar bucket of 100% silt, what is a common name for the texture of the resultant soil mixture? All right. So this is a question on ratios, right? So you've got bucket X mixed with another bucket, but this time around the bucket has 100% silt. What is the resulting mixture, right? So now you've got 100% silt. Let's convert the percentages into imaginary units, right? So here, out of a total of 100 imaginary units, okay, you've got 60 units of sand, 25 units of silt, 15 units of clay. This time here, out of 100 units, you've only got 100 units of silt. So what are your total, ratios out of 200? Okay, 60 to 125 to 15. Okay, so that is, totaling 200 units. But remember, in order for us to do this graph, everything is expressed as a percentage that needs to add up to 100 clearly. Okay, so 60 to 125 to 15, we need to divide all of this by 2 so we can get the percentages. So what percentage is it? Well, 30 divided by 2 is 30%. Sorry, 60 divided by 2 is 30%. 125 divided by 2 is 62.5%. And 15 divided by 2 is 7.5%. Okay, so let's find something with 30% sand, right? 30% sand puts us in this plane. 62.5% silt, which puts us in this plane, right? And then 7.5% clay, which puts us, like roughly in this plane right here. Okay, so we are in the transection of these 3 planes, meaning we're in the silty loam category. The answer here is C. Okay, what about question 2? So from a bucket of soil having the characteristics of X, this time all the sand's removed. What is a common name for the soil of the remaining mixture? Okay, so this time you remove all the sand, right? So what are you left with? You're left with 25% silt and 15, not 25%, you're left with 25 units of silt and 15 units of clay out of a total of how much? 40 units, right? Again, you need to express this as a percentage. So you need to make the denominator, this 40, 100, right? You need to get this up to 100. So how are you going to get it up to 100? Well, 40 times 2.5 is 100. So 15 times 2.5 is how much? 37.5. So 15 times 2.5 is 37.5. 25 times 2.5 is 62.5. So the new combination is 0% sand, right? So in the 0% plane, meaning we're only in this edge, okay? 62.5% silt, meaning again, we're here, so to speak. And 37.5%, 37.5% like clay, so to speak, right? Yeah, 37.5% clay. So basically, we're just right here. Okay, so in the silty clay loam territory, hence why the answer is D. Okay, so question 1 and 2, they were designed to test your firstly understanding of the axes and getting the orientation right, and secondly, can you do basic ratios, right? Okay, let's move on. Let's actually get to the cognitive loading. Figures 2 and 3 shows the distribution of and numbers in the crab populations of Exmouth Gulf, right? So this is the distribution of and the numbers of crab populations in a new location called Exmouth Gulf in Western Australia. In relationship to the texture of the sediment within the habitats for the crabs listed in Figure 1. All right, so Figure 2 is based on the bottom left corner of Figure 1. All right, so Table 1, a bunch of different crab populations. And then Figure 2 is where those crab populations lay, right? Now, the way cognitive loading works, I reiterate, is the principle of carryover, tracking a common variable, right? So between Table 1 and Figure 2, what's our common variable? Well, look at Figure 2. This is very similar to this right here, okay? Look again, right? What is this figure comparing? Percentage clay and percentage sand. Look at the shapes. Look at the topology of the different boxes that they've indexed this corner with, right? This topology, this axes representation is identical to this corner here, percentage clay, percentage sand, right? So that's how it's relevant. And the new variable that's been introduced is the different populations that exist in this geography, right? So that is how you would carry over, and that's how you are giving contextual relevance. Okay, that's how cognitive loading works. All right, now we have this diagram on top of that. Okay, so this time around, we've introduced a new variable, and that new variable is fine sand versus coarse sand. What we see here as well is that on the x-axis, you've got percentage sand, but on the y-axis, you've got percentage sand and silt, right? So, you're converting a three-dimensional diagram to a two-dimensional graph now. Okay, it's a very different sort of graphical representation of the data. Okay, so carryover principle this time is, the clay and silt and sand, they would probably have to add up to 100% because again, you're anchoring it to that very first data stem over here. All right, so let's do some of these questions, right? Question 3, what is a percentage silt in the habitat of Uka pavo? All right, so where is Uka pavo in table 1? All right, it's 11. Where does 11 sit? 11 sits over here, right? So it asks you for the percentage silt, okay? So to get that, we need to basically, again, track the three axes orientation that we did earlier. So clay reads horizontally. Clay is around 15%, therefore, right? Sand reads oblique down right. It's around 50%. Okay, so 50 plus 15 gives you how much? 65. So you can say that silt is around 35%. Okay, so what's the closest answer to 35? It's C. The answer is C. All right, what about question 4? Figure 3 shows the relative number of crabs of each species found in the 11 respective colonies. The species that has the greatest average number of crabs per colony in coarse sand. Okay, so emphasis, greatest average number of crabs per colony in coarse sand. Okay, so this is referring to this table here, right? So what do we notice about this graph? You've got like a central axis here. Below that axis, you've got coarse sand, and above that axis, you have fine sand, right? What else do we notice? What we notice is that, well, the question's asking what has you've got a bunch of these numbers, right? 1, 2, 3, 4, 5, 6. So these numbers correlate with the numbers here. So that's how you're sort of tracking that variable from above and giving it contextual relevance, okay? Because these numbers correlate to specific crab populations, right? So question 4 is asking, okay, figure 3 shows the relative number of crabs for each of these species in those 11 respective colonies. So what species has the greatest average number of crabs per colony, okay? In coarse sand. So in coarse sand, we can see that the greatest number is 1 and 3, okay? So let's track up 1 and 3. What are the numbers 1 and 3? So 1 is for O ceratophthalma, right? And 3 is for Mojberg. But notice the question asks you for the average, and Mojberg also has the number 2 attached to it, right? So if it's got the number 2 attached to it, let's track the number 2. Clearly, that also exists in this table. And in fact, if you had to do the average, what does it do, right? Having a 2 here that's slightly before the 3, which also belongs to Mojberg, it actually decreases that average. So it brings the average down. So what does that mean? The average of 2 and 3 is here, right? Meaning that the Mojberg average is actually lower than the ceratophthalma because there's only one population of ceratophthalma. Hence, the answer is D. Okay, which species has the greatest average number? It's ceratophthalma, right? Okay, question 5. This is a really annoying question. I'm going to leave this to the end. Yeah, I'm gonna leave this to the end. Okay, I'll just, preface it now and explain why it's annoying and also why it's very unlikely you'll ever be asked a question like this. Okay, consider all species shown in figures 2 and 3. The ratio of the number of crabs who are found in coarse sand to those found in fine sand is closer to what? So why is it annoying? Because you basically have to now go and count all of these numbers in coarse sand and then count all of those numbers in fine sand and figure out what has a greater population size. So what's more relevant, what's more abundant, how much it's more abundant by. It's a lot of mechanical thinking that is not very useful for a doctor, especially with AI being a thing nowadays. Like doctors do not do any of this mechanical work. We literally just get ChatGPT to write our letters for us nowadays, which is good because mechanical work is literally what a computer is designed to do, right? But anyways, I'll do question 5 at the very end, so don't worry. Okay, question 6. The equation of the central line in figure 1 could be best represented by what? Okay, so here we have a central line, right? And it's asking us to format it into an equation. So how would we do it? Okay, well, it's very easy to go with our y equals mx plus c model, right? Because that's what we've been taught in high school. Okay, and if you did this, then you can clearly see that C starts off on a 0 because you've got to be mindful of your axes. That's super important when you're doing graphs, right? So let's actually look at the axes, right? What do we note about the axes? Okay, goes up to 50, goes up to 50. Okay, so it starts at 0, meaning plus C is 0, right? The gradient M. The gradient M is kind of weird here, so to speak, right? Because with sand, you're starting at 100 and you're decreasing down to 50. And with clay and silt, you're starting at 0 and going up to 50. So automatically, the axes should throw you off a little bit. So to the careful, inquisitive mind, okay, who will consider the axes, you know that it doesn't fit into your typical y equals mx plus c because of the way that this ascends and this descends, right? So what else do we notice? We notice that, well, it's a linear line, so it doesn't have tricks to it like logarithms or like exponentials, right? But there must be a relevance for why this is ascending and this is descending. So the 25, let's just, track it. 25 and 75. If you add it together, how much is it? It's 100, right? What about this line here? 0 and 100 add up to 100. 50 here, okay, if we get our hypothesis right, should add up with the 50 and give you 100. And that's exactly what it does. So really, what you have here in the axes is a common variable, a cognitive load from all the way up here in your diagrams because percentage clay, silt, and sand together must add up to 100, right? So if that's the case, by sort of shorthanding it here and telling you clay and silt, they've advanced that argument forward that it still adds up to 100 regardless because you're still considering the silt. You're not excluding it. You're just combining it with the clay now. So what's the best formula? Well, you know that y equals x isn't right anymore because of the variables. Y equals x plus 100 isn't right either because it's not plus 100 in terms of, starting at a plus 100 on the y-axis. Okay. What about C though? X plus Y equals 100. That is very accurate, I would argue, because at the end of the day, no matter what Y point and what X point you're adding, all right, and selecting, they're all adding up to 100. So that's why the answer to 6 is C, all right? Now we're up to the final stage of our cognitive loading. Table 2 shows relationships found amongst crab species at Northwest Cape, Western Australia. So previously, you're dealing with crab populations in Exmouth Gulf. So now we're dealing with crab populations in a brand new location, which was hitherto not discussed, right? So in question 7 to 10, hypothesize that the data from Exmouth Gulf also applies to Northwestern Cape and vice versa. So basically it's saying that everything that we've learned hitherto also applies here in terms of whatever logical relationships. Okay, so this is sort of like it is somewhat of a lazy attempt at cognitive loading. Normally speaking, ACER GAMSAT wouldn't have even gone up to this stage. It would have just maxed out at like 6 questions and called it a day. It wouldn't have even included that fifth question here. So it would have just maxed out at 5 and called it a day. But here, because we're dealing with a different company, you have an additional question stem, all right? So Northwest Cape, all the data from before and the logical rules apply to this, all right? So what do we notice? How do we seek relevance, okay? Tidal position is a new variable, habitat's new, food's new, respiration's new, but crab species, maybe there are some things in common with what we saw above, right? So let's bring the crab species from table 1. Let's bring the crab species from table 1 down below and look for relevance, okay? So what is the relevance that we see? Okay, we see that ceratophthalmology, right? That's in common. We see that elegans is in common. Mossberg is in common. Flammula is in common. Pollard is in common, okay? So all of these species, so I'm just like comparing really quickly here. Mossberg, Pollard, Flammula, elegans. The only two that aren't in common seem to be Capricornus and Pavo. So with these in common, we can basically carry those forward to draw some kind of relevance between all these new variables and, the questions asked before, like coarse sand, fine sand, all those variables introduced earlier, like the geography of the nature of the sediment of the soil and all those variables. Okay, so question 7. From the data given below, the beach at Northwest Cape is likely what? All right, so the beach at Northwest Cape, you have ceratophthalmology. All right. And the beach here also has Mossberg. Okay, so ceratophthalmology and Mossberg. Ceratophthalmology is 1, Mossberg is 2 and 3. So 1, 2, and 3 belong to the far bottom left corner of clay and sand, right? So then if you were to track this above, what is this corner? What is this corner called? This corner is called sand, right? So from this data, the beach is likely to be sand. Okay, so that's an example of cognitive loading because you're looking at a common variable here and that's being the population. You're tracking it above, then looking for another common variable here and then tracking it above. Okay, so that's, at least 2 chains of tracking that you've just done. Hence why very common, very useful, very applicable GAMSAT question. Question 8. The salt marsh at Northwest Cape is likely going to contain what, right? So the salt marsh at Northwestern Cape. The salt marsh at Northwestern Cape, what's in common? Elegans, right? So what do we notice about elegans? Elegans is number 9 here, and number 9 is this one here, right? So what do we notice about elegans? Well, elegans is basically like you could say, I don't know, 20% clay, right? And it's still around 50% sand, right? So 20% clay, 50% sand. That leaves you with 30% silt, right? So there's probably like 30% worth of silt that you have to like investigate. So the salt marsh, Northwestern Cape, likely contains between 25% and 50% silt. All right. So 30% just falls in that range. Best answer. Okay, question 9. From the data, Uca capricornus and pavo are likely to include what in their food? All right. So previously, remember, from the analysis that we did, Uca capricornus and pavo were not common variables. They were not common variables. So I'm bringing this table down once again. Okay. So capricornus and pavo were 10 and 11. Okay. So you've got like 10 and 11. 10 and 11 also sit here. But notice how 10 and 11 both exist in the same soil sediment mixture as number 9. And number 9, elegans, that does in fact exist in this Northwestern Cape, okay? Elegans eat blue-green algae, diatoms, and bacteria. So because of that common link, you could argue that Capricornus and Pavo also eat this very diet, okay? So the blue-green algae, so to speak. And last cognitive loading question, question 10. The tidal banks at Exmouth Gulf are likely to contain what? What kind of sand? All right. So tidal banks. Tidal banks here. And what populations do we have? Elegans, Modgeberg, Flammula, Polydor, right? So those correspond to 2, 3, down to 7, down to 9. Okay. So yeah, so from 2 to 9. Okay, so it's quite the range actually, quite the range that's being captured here. But 2 to 9, and we need to figure out what percentage of like coarse and fine sand that they belong to, right? So 2 to 9. So 2, 3, 4, 5, 6, 7, 8, 9. So, like 2 to 4, there's more coarse sand. Then the others, there's more fine sand, right? So basically, the tidal banks seem to contain both a mixture of coarse and fine sand. So it's not just one kind of sand that's predominating. But see how in option C and D, there's this additional comment, additional qualifier on well mixed or not necessarily well mixed. The thing is, we've read the entire stem, right? And we haven't at any stage come across this logical rule about being well mixed or being not well mixed. So this is just extraneous information that you can't comment on. So for that reason, the answer here is D. It is not necessarily mixed because we don't know. It could be, it couldn't be. Who knows? Not necessarily includes that ambiguity, right? So this is just another tip. Don't choose answers that are like extreme qualifiers, like all, every, none. Like that kind of stuff is red flaggy for the GAMSAT. So that actually captures cognitive loading because that captures this idea of tracking common variables and how to link new variables that you haven't seen before in the context of old because you've carried forward and tracked common variables that link different data sets, right? As promised, I'm now going to go down to question 5, okay? So consider also figures 2 and 3, the ratio of the number of crabs who are found in coarse to fine is closest to what, right? So, I mean, there's many ways of doing this, right? One way is, for instance, canceling. So what can we cancel? We can cancel, like, say, 9, 10, 11, right? They're a bit more heavy on the fine sand, a bit less heavy on the, on the, you know, on the coarse sand, right? What else is a bit more heavy on the coarse sand and less heavy on the fine sand? These ones, right? Like, these populations seem to capture that essence pretty well, in my opinion, right? So, for instance, you can cancel these. You can cancel these ones out because it's sort of just a rule of approximation. So what are you left with now? What you're left with now appear to be 8, 4, 3, 2, 1. Okay, so you've got, quite a few populations. So another thing to be mindful of is that yeah. You've just got quite a few populations. So at the end of the day, the way you're meant to be doing these questions is just you add things up, you cancel it out, and then you see what's in excess and what's not in excess. There's a lot of math that goes into this. And I qualify it again, it's very unlikely that you're going to get this question asked to you. The answer to question 5, once you do all of the math and do all that working out, is C. Okay, so if you got C, good job. If you didn't get C, there's no big stress. I really wouldn't worry about question 5. I can almost guarantee 100% you're not going to be asked a question with this level of mechanical thinking. What you will be asked, however, are the remainder of the 9 questions, okay? And so the focus for this particular question stem is cognitive loading. And now you finally understand how this principle operates through interconnected diagrams, tables, and graphs, with the principle being you need to track the common variable to give relevance and context and link all the separate independent variables. Very high yield. This makes up at least 60% of the GAMSAT.